Nuclear Energy by Robert, Tom, Moulik, and Ricardo. Nuclear energy. What is nuclear energy? Nuclear energy is the process of splitting atoms into two to generate useful heat and electricity. Nuclear energy is economical, safe, and clean form of energy. Unlike fossil fuel plants, nuclear plants do not produce any greenhouse gases into the atmosphere every year. Nuclear power is carbon-free and produces more electricity than any other renewable energies. Due to this, it provides more than 60% of carbon-free power across America. In addition, nuclear energy facilities are able to produce affordable energy, leading to a low price of electricity for households. Each nuclear facility creates an average of 1,400 to 1,800 jobs during construction and up to 3,500 during peak construction. Once in operation, a nuclear energy facility creates an approximately 400 to 700 direct permanent jobs. Nuclear power stations provided about 5.7% of the world energy in 2012 according to IAEA, also known as International Atomic Energy Agency. In addition, the IAEA reported that there are 437 operational nuclear power reactors in 31 countries. That's awesome, right? But can nuclear energy be created using any elements? The answer is no. No, it does not. Uranium is a common element on Earth and has existed since the planet formed. Uranium is radioactive because all its isotopes are unstable. The most common isotopes of uranium found in nature are uranium-238, which accounts for almost 99.3% of uranium. Uranium-235 therefore accounts for 0.7% of the element found in nature. However, uranium-235 is the most important element to produce nuclear energy and, unfortunately, nuclear bomb.
Protons and neutrons make up a nucleus, which is the foundation of nuclear science. Nuclear binding energy is the energy required to keep the protons and neutrons of a nucleus tightly packed together. Fusion and fission involves the disintegration or binding of elemental nuclei and isotopes. The difference in mass before and after the reaction can be acknowledged to the nuclear binding energy. Basically, nuclear binding energy is considered as mass. To calculate the energy released during mass destruction in both nuclear fission and fusion reactions, we use Einstein's equation that equates energy and mass, which is E equals mc squared. There are two types of nuclear reactions, fusion and fission. Fission is the splitting of a nucleus that releases free neutrons and lighter nuclei as the number of protons are changing in the nucleus. Particles such as neutrons, photons, and alpha particles are also released from the reaction. The fission of heavy elements is highly exothermic. The unique feature of nuclear fission reactions is that they can be contained and used in chain reactions. The chain reaction is the foundation of nuclear power. One of the well-known elements used in nuclear fission is uranium-235. When uranium-235 is bombarded with a neutron, the atom turns into uranium-236, which is even more unstable, resulting in the nucleus splitting into daughter nuclei such as krypton-92 and barium-141 and free neutrons. The byproducts of a fission reaction are highly radioactive, as the unstable uranium-236 also releases gamma radiation and therefore difficult for waste storage. Contrariwise to nuclear fission reaction, nuclear fusion reaction is the process of joining two nuclei to form a heavier nucleus. Moreover, fusion of a nuclei with lower mass than iron releases energy, while fusion of nuclei heavier than iron generally absorbs energy. This trend is known as the iron peak. In addition, extreme conditions must be met in order for the reaction to take place. The elements must be in a really dense environment and the atoms must be moving at very high speeds. Also, extreme high temperatures up to 15 million degrees Celsius must be reached to force the nuclei together. It takes so much heat to achieve a nuclear fusion reaction even for light elements such as hydrogen is because in order to overcome the electrostatic repulsion by the protons of both the hydrogen atoms, both of the hydrogen nuclei need to accelerate at super high speeds and get close enough in order for the nuclear force to start fusion. The result of nuclear fusion releases more energy than it takes to start the fusion, so delta H of the system is negative, which means the reaction is exothermic. The reaction therefore releases the energy in the form of heat and radiation. The power of the energy in a fusion reaction can be observed in the natural world, as fusion is what drives the energy that is released from the sun and a lot of the stars in the universe.
Now that you're all filled with some energy from having a look at some general things about nuclear energy, let's explore some of the applications that may occur in the real world around us. Nuclear energy can be found in almost every field of research, from medicine to agriculture. The many different applications of nuclear energy exist due to a special part of nuclear energy, which is known as radioisotopes. What are radioisotopes? Well, to answer what a radioisotope is, we must first learn what an isotope is. Isotopes are different forms of an atom with the same chemical element. They have identical chemical properties but a different relative atomic mass. While the number of protons is the same, the number of neutrons in the nucleus differ. Isotopes are sometimes referred to as stable and unchanging. While most isotopes are stable, there are some unstable isotopes since the nucleus changes over time. Since the unstable isotopes emit charged particles or waves, this causes them to be radioactive. Due to this instability, they are referred to as radioisotopes, which allow them to have many use in today's modern science and technology. So their radioactivity is used as a tag to follow the movement of materials incorporating them. The many different applications of nuclear energy are food and agriculture, insect control, water resources, medicine, and the many uses of nuclear energy in industries around us. In food and agriculture, radioisotopes can be found in two things, which are fertilizers and increasing genetic variability. Fertilizers have two types of isotopes, which are nitrogen-15 and phosphorus-32. These isotopes manage how much the plant takes up or loses. It also manages the amount of nitrogen that the plant takes in from the air or the roots. Increasing genetic variability is the process of using radiation to induce mutation to plants in order to produce new genetic lines of root tuber crops, cereals, oilseed crops, and many different vegetables and plants. Insect control involves a special technique called serialized insect technique, or also known as SIT. This involves nurturing a large number of insects, then irradiating their eggs with gamma radiation before they hatch to serialize them. When they mate with females, no offsprings are produced. With repeated release of SIT, the population of insects are reduced.
Another use of nuclear energy is space exploration. Plenty of unmanned spacecraft obtains its power from radioisotope thermoelectric generators, or RTGs, including the Galileo spacecraft mission and even the Mars Curiosity rover. This type of generators harnesses the heat from the decay of plutonium. The advantages of using this are that it is very safe, reliable, and robust. Another use for nuclear energy is water desalination. Furthermore, it is essentially removing the salt from salt water. Water desalination is not a new thing. However, it is usually done with fossil fuels. The problem is that it's still very expensive. Fortunately, nuclear energy can decrease the cost, resulting in affordable drinkable water for more people around the world. Nuclear energy is not perfect. It has some of its disadvantages too. The construction of nuclear plants can be very time-consuming and expensive. Waste products can be very dangerous if not handled properly. Elements that are often used to extract nuclear energy are very scarce. However, the advantages of nuclear energy outweighs its disadvantages. The first advantage is that it's the largest source of energy with minimal pollution. It emits very little to none greenhouse gases, which avoids problems such as smog and acid rain. This is important because it can help maintain water quality and habitats of animals. Another advantage is that nuclear energy's life cycle emission is significantly lower than fossil fuels and natural gas. Life cycle emission is the emission of carbon dioxide of this technology starting from construction all the way to dismantling. A big advantage of nuclear energy is that it produces a lot of energy from a small amount of mass. For example, the fission of uranium-235 produces energy equivalent to 60 million times the burning of carbon atom. This is shown in the famous equation of E equals mc squared. Just remember, c, or the speed of light, is a big number, and it's even bigger if you square that number. Last but not least, nuclear energy is very reliable because it can run 24/7, even in rough weather conditions too.
Created using Powtoon.